Look, and look at this. We have a new eraser.
Oh.
It says S104, don't take Scots. And it looks that's dry erase pen. So I might try it out to see how well it works, even though it's Scots. This is technically week 3.
But it's really like.
It's really like the end of 2. If we'd started on the Monday and hadn't had a holiday,
Right.
we've covered the same amount of material as.
You can reach it from here? Yeah. Please start here.
All right. So we have one last mechanism to go over for alkenes, and then we're going to start talking about alkynes. So our last, sorry, I just blanked, make sure that I did. Okay, I did hit record. Our last mechanism is called oxidative cleavage or ozonolysis. I showed this to you the other day. And gist of it is it's always going to come down to you find a carbon-carbon, pi bond, and single bond, and what's unique about this is it cuts both of them. Which is weird. So this is our first reaction that actually changes the carbon skeleton of a molecule. So far, everything has just been find the functional group, modify the functional group.
Right.
This one, actually, you can change what carbons are part of the molecule entirely. We mentioned using this. We use this a lot for breaking down a lot of organic material because most organic material has carbon-carbon pi bonds.
Right.
So we see this a lot as a way to basically just break stuff up into smaller chunks that then could be removed easier. So water quality, water purification, but also just as a way to sterilize things. It won't remove completely the organic components, but it definitely kills everything that's in it. And so our mechanism for this is one of the trickier ones because it does have several rearrangements that happen and multiple steps that all have more than one arrow at a time. So the first step with ozone, one of the tricks is recognizing why ozone is so reactive is because it has this bent structure. And this bent structure means that it's kind of positioned so that both of these oxygens can react with the 2 carbons simultaneously. And so what you get is a lone pair from one oxygen moves towards a carbon, a pi bond from the other carbon, or the pi bond between the carbons moves towards the opposite oxygen, and then you break the oxygen-oxygen pi bonds. Right, so this ozone does have a resonance structure, so it's kind of arbitrary which direction the electrons are moving, because this molecule has that resonance structure that's going to look like just moving the pi bond to the other side.
Oh, yeah.
If we started from this resonance structure, we'd get the same product, but we'd have the arrows drawn in the opposite direction. But there's no net difference between them. So the important thing is that you remember that the oxygen-oxygen pi bond moves towards the middle oxygen. If you use that to set the direction that the arrows are going, then you shouldn't mix it up too bad. Right, because then everything else is going to fill the void that's created by moving that pi bond, and then fill the void, etc. So then this makes a molecule that's kind of like an oxide, but it's even shorter lived. Called a malozanide. Which is just this 5-sided ring structure. So again, very similar to an epoxide, is that we have 3 oxygens, so we can make a 5-sided ring instead of 3-sided. So it looks a little bit more stable.
Is it?
Not really, because it will spontaneously rearrange, because this has 2 peroxide bonds in it, right? Peroxide bonds are inherently pretty unstable. And so it does this weird sort of rearrangement where you wind up turning it temporarily into 2 carbonyls. And then it rearranges to make the more stable ozonide, which is still a 5-sided ring, but it basically breaks the carbon-carbon single bond so that we can avoid having a peroxide bond. Right, so lone pair for the oxygen moves towards the carbon to make a carbon-oxygen pi bond. One of the peroxide bonds moves towards that side to become a lone pair. The carbon-carbon sigma bond turns into another carbonyl. So if you're setting, this is another one where the direction of the arrows is kind of arbitrary. You could have written this opposite. The main thing is just pick a direction for your carbon-carbon sigma bond to move. It's always going to move towards an oxygen, and then set the rest of the arrows after that.
Which?
So if you start with the carbon-carbon sigma bonds, move it towards an oxygen. Pick one of the 2 adjacent oxygens and move it towards it. But in order to do that, you have to make room. So you want to push electrons around to do that. And so if I was writing this from scratch, just for fun, we'll go the opposite direction. We say, okay, if we're going to draw this towards this oxygen, we now need to make room for that so that we don't have an oxygen with 10 electrons. So that breaks a peroxide bond and turns it into lone pairs. And then one of the other lone pairs over here moves over and becomes a carbon oxygen bond. So for this whole first step, every single one of these steps is 3 arrows at a time. You have 3 active pairs of electrons in each of these steps. And they're always moving in sort of a ring structure. So they're kind of chasing each other in a circle. So after this second step, we actually temporarily break up the whole thing. But it just sort of reshuffles. And you wind up with the oxygen is part of a peroxide bond still. Winds up acting as a nucleophile and attacking, there's a partial positive here because it's carbonyl, right? So basically this negative charge is going to move towards that, which then means you've got to make room for it so we don't have a carbon with 10 electrons. So then that carbon-carbon pi bond also acts as a nucleophile because this other carbonyl also has a partial positive, right? Because carbon oxygen bond. But then to make room for it, we do the same thing. Push that carbonyl bond. It just becomes another lone pair. And so the result of that is our stable ozone. These are both considered ozonides because it's an ozone attached to what was a alkene. But this malozonide, the initial ozonide, just breaks down. It does this rearrangement so quickly. It's an unstable ozonide. This one's stable. You can actually isolate it. We need to actually add a reducing agent to break it up.
And ozone is the product.
Ozone is, where's it written? The O3.
Okay.
This one. I knew I had it drawn up here somewhere.
Yes.
And so an ozonide is just you stuck an ozone on top of an alkene, and you started by making this, the obvious one, but then it does this weird rearrangement to make this five-sided ring where you've broken the carbon-carbon bonds.
Yeah.
This is more stable than the initial ozonide because we basically lose a carbon-carbon sigma bond, but we also lose a peroxide bond. Peroxides are so unstable, it'll do this weird rearrangement because now we only have one peroxide bond. And then this step 2, like we've seen in several of our other mechanisms, step 2, a lot of these reduction reactions, the mechanisms are beyond what we need for this class, so we basically can wait the second step. So being able to get to here is the part of the mechanism that you actually are responsible for knowing.
Okay.
And then step 2 is just mild reducing agent, which usually is DMS, dimethyl sulfide.
Is NMR? Mars? Or
Yeah.
is it kind of
This is not even an addition reaction. This is a whole new class of reactions.
what class?
It's the cleavage reaction.
We're gonna have more cleavage reactions.
There's at least one more.
So
2 more, because we're gonna do the same thing with alkyne. Yeah. So if your broadest differentiation for your reactions is reactions that change the carbon skeleton and reactions that don't.
Right.
This is our first reaction in that other category that changes the carbon skeleton. We're going to add a couple reactions that will add carbons, and we'll add a couple more where it allows to remove carbons. But that's going to be a smaller subset of reactions. For the most part, if we can get the carbon skeleton we want, most of it's going to be just, finessing the functional groups to be in the right spot.
So this is an ozonolysis reaction?
Ozonolysis. So ozone from ozone, and then lysis means splitting. Like cell lysing.
It's that word.
Yes.
I just want. How do we know if it's gonna be that we see it?
When you see an O3.
There. Is it always gonna be DMS?
Like this. DMS for zinc. Zinc is the other mild reducing agent that we see.
It's like, but we don't have ozone.
No. So ozone gets made in the upper atmosphere naturally because of the radiation from the sun.
Oh.
So it's naturally present in the upper atmosphere. It also gets produced, it's one of the main components of smog. And so so for a while, especially in the 80s, we were losing ozone where we wanted it in the upper atmosphere where it absorbs harmful UV rays. And we had too much of it in the LA basin, where it was just basically like settling in. If you've ever smelled the way ozone gets described, it gets generated by lightning strikes. Because lightning or current moving through oxygen basically will cause this to form from regular oxygen molecules.
So when you go like it smells like lightning.
It smells like ozone.
Arc and antiarc are addition reactions.
Bingo.
And then the neither both reactions are addition reactions.
Correct. This is our first alkene reaction that's not an addition reaction.
And it's gonna be
It's a cleavage reaction. You could consider it subtraction, I guess.
This one?
Yeah, or division.
This is division.
Yeah.
So I feel like elimination reactions are subtraction.
Yeah. You could say that.
Have you ever had a student compare these to cut glass?
I can't say that I have. All right, let's try Scott's turn. Curious. I'm not sure it's any better.
You gotta really push it forward.
No, Scott Valentine's way taller than I am. Yeah. All right. It's a good experiment.
Forgot. First, how long do I have to do this?
He filled up this full word grain as everything fine. So maybe he uses a spray.
Maybe, and that's why it's also like the law.
Mm-hmm. All right, so let's do some practice, some review of alkenes. This is our last slide on alkenes before we go to alkynes.
So this is practice with all of the arguments.
Well, look at what you got. We've got hydroboration. We've got epoxide and ring opening. We've got acid catalyzed hydration. We've got Rocco. We've got dihydroxylation, hydrogen. Yeah, we've got a lot of stuff in here. Finishing up with an ozonolysis. So I'll give you a few minutes on this, and then we'll start working through them.
We're just doing the products.
Yes.
CHM. Personalized. Trees. Okay, what's one thing about it? That double bond with the. If that positive charge is already on tertiary, it's not, right? Mars, so, this one. Yeah. This one back. H. That is from one from my church and one of my let's see. Is that we need to go on the first one. All the related question with movies. Either or both. Anti-dihydroxylation observation. Oh, yes, because we add two. On both notes. Three of each. Um. Probably over there. So that's what we're going to do. So. Yeah. Back up. What was the one of the just. Died and lost. That's the.
That's good though.
Instead, see, I spell by myself. I spelled pterodactyl. Amazing. Yes. Yeah, it says OS 04, but that's my design with two. That's yeah. Good job. That's what I'm trying to get was the last of my ordinates. But one of the difference. They're both coming towards us too. They're not going up. They're coming out through us. The arms. That's the top to the right. I feel all you do is take a real.
You hydrogenate it, so you break the pi bond to make more carbon hydrogen bonds.
We just replace it with hydrogen.
Yeah, exactly. But since we don't draw hydrogens in our skeletal structure, it looks like, yeah.
So the last one was sin. I feel like we're doing pretty good though. That's the stuff I mean. Oh wait, that's the second. Yes.
And how do we switch the hydrogenation from being our problem from anti?
When
That's not what we're doing, sorry. I won't interrupt you. We'll talk about that when we go through these.
most. So is this one? Is that statement solution? And come on, I will find it out. Is this similar to what we should expect to assess?
So just like just like all my classes, I'll give you a practice test ahead of time. But it'll be pretty similar to the final where there's a couple mechanisms or 10 points apiece, and then a couple pages. There's probably, I think I usually do 10 reaction products like this. So this is 10. So this would be like 40% of the test.
Okay.
Because each one of these would be worth 4 points is usually the way I score it. So then 70% of your midterm is going to be 3 mechanisms and 10 reactions.
Do you want us to draw like this with this? Like, the replay, so you want us to draw it like before the step, we don't know, or after?
After, because it has step 2 drawn, you could draw the intermediate if you wanted to draw the other side. But what I'm actually asking for is after that second step.
We don't think that. Well, if it's when the ozonolysis.
Ozonolysis. Yeah.
Always.
The product is always, the net product is always break both bonds and replace carbonyls with carbon oxygen double bond. So this one's a little bit tricky in that it has 2 pi bonds.
So we're gonna have 2 products.
Bingo. You're gonna have 2 products no matter what with these,
But 2 different,
but
like not just reverse, like.
right, it's not symmetrical.
Yeah.
Yeah. Give that a try and start working through these.
We have 1. That's good.
A little warm.
That's what I did, I don't know if it's right. Are you missing one?
No, I just put space. Great. Hydration. And anti-metabolic health.
Yes.
Got it. Epoxide formation followed by ring open. So the net is that anti dihydroxylation. And this is definitely what we want to pay attention to because we're making stereo centers when we do this one. So we gotta be careful because we're gonna make 2 different stereos.
Okay.
So we gotta be careful which one, and we're making 2 stereo centers. We gotta be careful, we're only writing the enantiomers we're actually gonna make. So we could make the methyl here down and the OH up, which would then put the OH down over here with the xanthine.
This is supposed to acid and respiration.
No, CO3. So that's Rocco,
Yeah, which is
anti-dihydroxylation. If you made the epoxide facing downward, like, rather, we're just going to wind up switching the OHs. So we're not making every stereoisomer possible. But this is definitely where you can't just say R plus S because there's 4 possible stereoisomers, we're only needing 2.
right.
You could say this one plus EN because both of these stereocenters get flipped.
They would never be fixed to each other.
Not the OHs will always be trans because it's anti-dihydroxy. Anti means that are adding opposite sides. Oh, but I left off the OH here. This one's just acetabulized and no rearrangement here, right?
Right.
But that's stereos,
So R plus S.
R plus S.
What is the S? I know R is right. S is
Sinister.
right. It's left is E.
Yes.
Do you not?
It's actually backwards. The word sinister derived from it meant left-handed before it meant.
Oh, so maybe that's
So
we're just equal. So
that was the Dark Age superstition. So after the Roman times, when they first established in Latin that sinister meant left, in the Dark Ages it was a superstition.
what about people that were?
They would have had to. I mean, for the most part, during the Dark Ages, the average person wasn't right. So in general, they didn't necessarily know who was left-handed or right-handed if you're just doing manual labor. But they actually thought, so before they had clockwise and counterclockwise, before they had clocks, they used a term for counterclockwise called widdershins. WIDDER. Widdershins meant spinning, meant something was moving counterclockwise, and that was associated with witchcraft. They thought that the covens of witches were having black masses in the woods where they were dancing widdershins around the fire. Widdershins. I don't know what they call clockwise, but I know what they call counterclockwise. It probably had to do with the sun, because one of the reasons that widdershins was seen as being evil is was going opposite of the sun. And left-handed.
This evil people.
All right, we've got another Rocco here.
Yes.
Another epoxidation followed by ring opening. And so I'm actually going to draw the intermediate this time just for practice. After step 1, we made the epoxide. And then step 2,
Hydrogen.
that oxygen comes in from the other side and breaks this. So we're still going to pay attention to what stereoisomers we're forming. We're going to get that plus the enantiomer. Sorry, OH. OH.
When it's an OH, I know we're not drawing it, but it still technically has a lone pair on it.
Correct. There's 2 lone pairs on each of these oxides. We don't need to draw them because that's what makes them neutral. So we're inferring because it's neutral, it also has 2 lone pairs. And then for I, it's going to be syn dihydroxylation. So these ones we need to be careful. See, that's 7. 1, 2, 3, 4, 5, 6, 7. If we put both methyls down, then we can put both OHs up. Plus EN, which we're drawing. Gonna look like methyl up, OH back, methyl up, OH back. All right, so if there's one takeaway from this first set of 5, it's that the stereochemistry is where it gets really fiddly, complicated. But remember, each of these is worth 4 points on the test. 3 points would be just getting the right product and forgetting about the stereochemistry. And if you attempt the stereochemistry and get it wrong, I can still give you partial credit on that. So that'd be like 3. Getting, I mean, unless you're like egregiously wrong, in which case points for it. But 3 out of the 4 points is what functional groups am I adding for? And then the last point is, did you get the stereochemistry?
No, we don't get a cheat sheet for the midterm, but we get one for the time.
We'll talk about it. I gotta go back and think about what I did in the past. I have to see if I have any notes anywhere on that. We're definitely getting to this. I think by the midterm, we probably have just gotten through alkenes, alkynes, and then there's a whole chapter on synthesis using what you know so far. Like, how do we make this out of the pieces and the reactions we have? So I'll think about it. Probably what I'll do is it'll be like you get, a half page of notes for the midterm and a full page for the final, and then we'll add on to that as we go into the 3rd term.
Sure.
All right, the other half.
Bruce does the same thing and take brings it down a little bit, so you can see it.
Well, because there's part of the slides are there. It would be fine if I was trying to use the whiteboard and the projector at the same.
Yeah.
We tried that upstairs in the big room upstairs, but they just painted the wall with whiteboard paint, but they didn't smooth it first, and so it doesn't work very well. Okay. And it's way too big to actually reach.
Yeah.
So we tried. at certain times. This is better than most setups on campus. I prefer this to most because I've got more room than smart boards.
Right.
Anyway, this is another one where we've got to watch out for stereo chemistry.
Okay.
But other than that, we're just breaking the 5 but it's a standard addition. So both of your hydrogens are going the same direction. Correct. But because this is not a symmetrical ring, we're going to wind up with some stereo chemistry. So we are going to do this, but if we wind up with, I'm going to draw the hydrogens even though we don't usually.
What difference?
So this one's a stereo center, but doesn't really matter in this case. If we had another method for here, it really would matter. Because we only get the 6 isomer at the end. The other way that the 2 hydrogens could add, both hydrogens going backwards. There's our new hydrogen, there's our new hydrogen. So once we have them drawn, you can just erase the hydrogens. This is definitely a case where in some we're not going to be super picky about skeletal structure, never showing hydrogens because the hydrogens are the active atoms. So sometimes it's to our advantage to draw the hydrogens in their stereochemistry, even though normally we ignore them, because they're what's actually so if you drew it like this and just left it like this, that'd be full credit, even if I said skeletal structure.
Okay.
Because that's the active atoms.
Yeah. This is in
Metal in the board, OH out of the board, OH out of the board. Plus here. So far, so good?
Yeah.
After the catalyzed hydrochromation. No rearrangements to worry about. And it's Markov tunnel. We do want to think about rearrangements. That's that lies.
But it's not gonna happen.
That's not going to happen because we're already going to make a tertiary carbocation. And it's symmetric around the ring, so there's no anything for that. I also feel like I should say in this case that you don't want to just spam plus EN on everything, because if you write plus EN and there is no enantiomer, or the enantiomer is the same molecule, then there will be a small deduction, a quarter of a point, because you're not like, yes, you will also get the mirror image, which is the same molecule,
Right.
but you can't just get away with just saying plus EN every time. Because sometimes there isn't an enantiomer. Sometimes the mirror image is the same molecule. And this is one of those times. Because it's symmetric around the ring.
Yeah.
The one reaction that we've covered that wasn't on this page, though,
done.
or
Yes,
same net result, except it's anti-Markov.
okay.
So if there was a peroxide there. We're putting VR here. Which now it does happen consumer because. And you know, we got 4 different things attached to that series. There you could put plus.
Wait, one race.
Okay. You're back. My tendency is to go fast until somebody tells me to slow down. So I rely on telling me that they want me to slow down. Okay. Another hydroboration.
Wait, so what is the one that everyone's up for?
So that would be the radical hydrobromination, or you say the anti-Markov hydrobromination. Just adding that little bit of peroxide, it doesn't need, it's just like a couple drops. It doesn't take much. It's enough to switch it from being bromination to radical. Hydroboration is because we're adding boron and then oxidizing. So hydration, anti-Markov.
So H hydroboration.
Is hydroboration.
What actually is CHF? Like what is it?
Tetrahydrofuran.
R plus S again.
They mean the same thing. So because I didn't draw both, I didn't draw a specific enantiomer.
Great.
If I drew it like that, I would do plus EN. If I drew it without showing any stereochemistry, I would do R plus S. It's probably better to do the pick one and then do plus EN because that shows me you understand where the stereochemistry is. But you will see both of those. So this is furan. Tetrahydrofuran is basically get rid of the double bonds. So furan is aromatic. It doesn't look like benzene, but we'll talk about why it is later. So that's also a really common solvent as well. But this is a little bit less reactive. And so we use tetrahydrofuran as it's a really common aprotic solvent. It's a little bit higher boiling point than acetone, so it doesn't evaporate as easily. Acetone and THF and DMSO, which is dimethyl sulfoxide, are the most common aprotic solvents. So you'll see that it'll show up all the time. All right, last but not least, ozonolysis. All right, so the way that I usually approach these, like sometimes it's easy to see. When it's something like this, where it's a ring, it's a little bit trickier to get the right number of carbons, right?
Yeah.
So I would handle this one first. I would, give it one of those. You're going to get acetone from that top piece. And then this other piece is going to turn into a carbonyl as well. I would leave the rest of the molecule the way it is and draw it like that for starters. And then tackle this. Really, this happens simultaneously. It's not happening in 2 steps, but just to make sure we don't miss carbons. Then what I would do is I would take this and break that. And I'd add an O there, and I'd add an O there. That's fine too. It's just spatially, it doesn't, I don't like the way that looks because they look like they're on top of each other. The main thing is that then you can come in here and now we can count our carbons. 1, 2, 3, 4, 5, 6. So it's going to be a double aldehyde. So it's 1, 2, 3, 4, 5, 6. Aldehyde on this end, aldehyde on this end. And then 1, 2, 3 carbons in. Count from either side, it doesn't matter. It's our other oxygen. It's not too tricky, but if you rush it, it's easy to add a carbon or delete a carbon.
With these ones, every time you add oxygen, it's going to be double bond.
Correct. For alkenes. Alkynes will do the same reaction, except they make carboxylic acid instead. Which is, it's a carboxylic acid looks like this. So in that case, you are adding a carbon oxygen single bond as well. But basically, you're replacing all the bonds in the alkene with an oxygen bond.
So then the final result is the chain.
This is the final result plus that. You would get two separate molecules. You always get two separate molecules. It's the one time drawing it like this is fine too. As long as it's neat enough, I can see what's going on. The only time, this is the one caveat to this before we take our break, is if you wind up with a 1 carbon fragment when you do this, you don't make formaldehyde. So like for instance, we had just that molecule. We do ozonolysis. This piece is going to turn into acetone. This piece, it might look like we should do this to make the aldehyde. Typically, what actually happens is we're not actually going to see any of that. It'll basically just fully oxidize all the way to CO2. So we're not going to get single carbon fragments. Other than that, it's as simple as find your double bond, cleave it, take a cleaver to it, redraw it with carbonates.
Yeah.
Easy enough to say, can be a little tricky in practice. All right, let's take a break. Let's come back at 10 after. We'll talk about alkynes a little bit. It did. I'll grade the other one this afternoon. I'm going to endeavor to be on better about my grading this quarter as soon as I'm done with the high school. They take their final tomorrow. And then I have like 1 day turnaround because they expect final grades by the end of the weekend. So there were a few of them that, and also this is also a good time to remind you, you can, for whatever reason, sometimes when I write these questions, I split it up into 8 questions. You can always submit one file upload that has all 8 of problems on it. Well, it didn't used to make a difference because SpeedGrader on Canvas would actually display it. Now they changed it, and now you have to click and download every single file and reopen it on. So now it's even better for me if they're all on the same page because I didn't find it.
Yeah, each question asks us that the question.
So it can be the same file 8 times if you want. If you or just
let us turn it in without actually putting it in every slot.
And it's really just there's only 2 of these, so it's not that big a deal. And I just need to write the questions so that they're all on one question and it won't be an issue. But yeah, that's fair game too. It's just submit it all to one file.
I mean, I just screenshot Might make like 7
And if it's,
the other ones.
yeah, don't go to that much effort. If it's easier for you to submit a bunch of different files because you're doing it on your tablet, that's fine too. It's really not a big deal. Yeah, that's fine.
I knew this comments. Still has been working.
generally speaking. All right. And you actually have a few minutes even.
Blueberry commission. And you run out of the
Have you tried the Uncrustable makers?
You told me about them and I didn't list on the.
I think it's a good way to meal prep ahead of time because you can make like a dozen of them on Sunday
Right.
and then be set for the week. Plus you can mix it up. You can do Nutella or something. Which my kids have started getting into. They've started making their own sandwiches. They call them all peanut butter and jellies, but they mix and match. Like sometimes it's cream cheese and jelly. Sometimes it's cream cheese and Nutella. Peanut butter and banana. The cream cheese and jelly one is one that I grew up with. I don't. It's an old one from. I think it predates peanut butter. Okay. Cream cheese and salami is really. I think cream cheese is one of the best, most versatile cheeses out there, frankly. Yeah, that's a good one. I even will get it on, when you go to Tahoe Bagel and they have the breakfast sandwiches. I'll actually get, instead of getting cheddar on one of the breakfast sandwiches, get a cream cheese. It makes it really messy, but it's that nice creamy texture to go along with the sausage or whatever. Yeah, sushi is really good. All right. Now we're ready. So alkynes. They work the same way as alkenes. Just can't get it exactly right. There it is. It takes some finesse. So you name them the same way as alkenes. Except we say ion. So instead of one pentene, it's one pentyne. I think they use the Y to make it explicitly clear that it's not pronounced the same as E. So they use an I. You could really easily say phonetically that that's pentene also. So for whatever reason, it's pentyne with a Y.
Used to. And I already what?
I think so. Should be. The nice thing about pentynes is they are not sp2 carbons anymore. They're sp carbons now, right? Which means their geometry looks like what? These ones were flat too, so not just flat, but also linear. It's a straight, it's 180-degree bonding here. Because there's only two things taking up space around the central atom, right? Which simplifies things in some respect, because if you only have one other thing attached here, and it's 180 degrees from the alkyne, you have to worry about cis and trans or E and Z. No, because there's only one place something can be attached to that carbon. So that actually simplifies naming a little bit. However, it does mean that drawing skeletal structures, you have to be careful. Because it's really easy to get sloppy and make this look like it's all one thing. So that's why on the drawn ones, they actually do that to make it really clear. The other way that you see it is just drawing out that functional group so that you make sure you get the right number of carbons. This is the most common way, especially if you're using a computer program, but this is really common if you're doing it by hand. So let's do some practice naming things. What is that monster called?
Oh, God. Too much. As long as
Like without heat, it's gotta be the longest continuous carbon chain that has the function for everything.
listen.
Yeah, so it'll be a heptine, it'll be one heptine. And then it's just a matter of finding our branches. We've got 1, 2, 3, we've got propyl on carbon 1, 2, 3, so 3 propyl. Ethyl on carbon 4. And a methyl on carbon 5. 4 ethyl, 5 methyl, 3 propyl, 1 heptine. There's a joke in there somewhere about it sounds like Elon Musk and Grimes would name a child. And if you want to be as correct as possible, actually, I think we accidentally got it right. ELMNOP. We did put it in that order, but that just happened to be the way we. All right, so easy enough. Good review of how to review our IUPAC meeting. That's not going anywhere anytime soon. When we look at what this alkyne group looks like, we can compare it to an alkene. So an alkene, so this is simplest alkenes, ethylene, ethene. Remember ethylene is the common name for what we would name as ethene. So if you see this means the same as ethene. That's the proper name, that's the common name.
Why? I'm adding more letters.
You're gonna have to go ask somebody who's dead because this is predates anybody who's alive. You would think that, so this came from before they had the IUPAC system. They had the naming, they had like the numbering, F means 2, but they didn't have like, here is our definitive way to name things. So ethylene here, it's trigonal planar in shape, right? So it's sp2, and we've got our pi bond. Our sigma bond is directly between the two. Our pi bond is where we get that overlap. An alkyne is going to look pretty similar. The only difference is it's got 2 pi bonds, so it has that same thing twice, which is part of what makes it linear. You basically have like a coating, a pi bond surrounding a sigma bond. And also, just so that you've seen it before, we would name this ethyne. But guess what? There's a common name. acetylene is what we would call ethine using our IUPAC system. This is both of these, they're common enough still outside of the chemistry world that you still see acetylene is actually more common than ethine is when you get outside of an OPEC phosphor. Because it's just the ultra weight it's welding gas. It's what you use to they call it an acetylene torch. You're using a torch to cut metal. You're burning acetylene with oxygen. So it's still really common. And then this ethylene, you'll still see ethylene used a lot, or just in biology textbooks. It's a plant hormone. And so it still gets used a lot by its whole name. And it also gets used, they actually use this commercially when you're shipping produce. Ethylene is the hormone that triggers fruit ripening. And so what they'll do is they'll pick fruit before it's ripe so that it's still nice and firm and hard and won't bruise. And then they'll ship it to a grocery store where they basically spray a little bit of ethylene on it. And that causes the ripening process to start. Also why, I think I mentioned this last quarter at some point, but there's a trick to get an avocado to ripen. Bananas works better. Apples will do it too, but apples have actually more complicated hormonal system. So they trigger being ripe by being in contact with other apples. So the phrase "don't let one bad apple ruin the whole bunch" actually means you have to physically remove the bad apple, or else they will all spoil. But I would use this. All right, so C2H2, also known as ethine, also known as acetylene, is going to look pretty similar to an alkene, just linear. So what can we assume about the type of reactions we're likely to see? Similar. If the orbitals look similar, if it's still got carbon-carbon pi bonds, we can expect that it's going to go through a lot of the same reactions that our alkenes did, because carbon-carbon pi bonds. So the first one, the objective always started, this is how you make the functional group in the first place. The way we make an alkene was we did an elimination, right? If you have a diene halide, it can go through a double elimination. It just does an elimination twice. We just have to make sure we use a strong enough base that's not likely to do a substitution. So there's a couple that are favored very heavily. Most specifically, we're going to see sodium amide, NaNH2. Remember that NH2 with the negative charge? That's super strong base. It's got a pKa of like 30 something. So it's a really strong base, which is really good at causing elimination reactions. And it's actually such a strong base, it'll actually do it almost like a triple elimination. It'll do a double elimination to make the alkyne, but then that alkyne has that hydrogen is actually acidic, meaning we can deprotonate the alkyne if it's the end of the carbon chain. So if we have excess sodium amide, we'll actually go all the way to deprotonating the alkyne as well. Which then we just usually follow this up by adding water, and it just seals the hydrogen with water, and you get a terminal alkyne. So when I say terminal, I mean it's the end of the carbon chain. In fact, it does that so well that it actually can basically can ignore Zaitsev and Hoffman when we're doing this, because you're not going to make you're not gonna stop at the alkene, you're gonna go all the way to the alkyne. You'll actually rearrange along the process to make it a terminal alkyne so that it can keep protein. That gets a little bit tricky because there's some fine lines for well, how far can it rearrange and how much time before you call that reaction done. So for the most part, I'm going to stick to using this when we have our halides are close to the end of the carbon chain, so we don't have to get into the nitty-gritty too much. But this is the way we do it. Excess sodium amide in ammonia. We have to use ammonia as the solvent in this case.
Is water always going to be on the bottom?
Water's always going to be on the bottom. And remember, it's not just on the bottom, it's a whole separate step. You have to do this whole first step in the absence of water. Because otherwise, your sodium amide is just going to steal hydrogens from the water. It'll make an alkene first as an intermediate, but then it makes the alkene. It goes further. So it's going to do one elimination to make the alkene. And then we would still have another, so we would get something like this. We still have another bromine that it can remove. So it does it again.
This is just an alkyne elimination.
Yeah, this is the way we make the alkynes in the first place. They actually don't show up that often in nature. It's an elimination, it's just a double. So we don't think about things that often always going to go the end of the chain. So we actually make the intermediate here that looks like this. And then so step 2 is just adding water so that we can protonate it. So our final product is going to look like that. Then on this side, doesn't really matter if they're on the same carbon or not. They'll still go through elimination. We'll do the double elimination, deprotonate the carbon at the end, adding water reprotonates it. So we'll actually get the same. And then it's never a bad idea to just double check your number of carbons, because when you go from drawing them as angles to drawing them in a straight line, it's easy to add one or lose one. 1, 2, 3, 4. 2, 3, 4 plus the 2 metals.
I know, yeah.
All right, couple more things. This is just a good pKa table.
How do you get the triple is there to only 2 before?
There's already a single bond right here, so we're going to turn this 2 chlorines into 2 pi bonds.
On top of this.
On top of the single bond, sorry. Right, so this is just a list of really strong bases. So you notice water, hydroxide is all the way down here at the bottom. And all of our deprotonated alcohols, they all have pKa's in the 15 to 18 range. So they're strong bases compared to a lot of things. They're not strong bases compared to alkynes. We call this, when it's deprotonated, we call that an alkynide. So alkyne, and so we drop the E and write I. Just means this is this one. I just means that you deprotonated it in a lot of cases. It means it has a negative charge. So an alkynide is just an alkyne that's been deprotonated. So these alkynides are still pretty strong bases. They've got a pK around 25. So if we want to deprotonate it further, there's only a few options. This is the one we've already used. You can use hydrides to do this. If you have, I think the most common way to do that is we have sodium hydride. That's really unstable. And will basically it'll pull a hydrogen off of the alkyne and to make hydrogen gas. The problem with this is not shelf stable very much. Sodium amide is much more shelf stable. And so we wind up with that being the more common option is to use this. And it is a slightly stronger base anyway, so we do get even better yields. The other helpful thing about this, remember strong bases also were typically good nucleophiles, right? Because if it's super unstable on its own, it has a negative charge, it's going to seek out a positive charge. Which means this is actually now a way that we can add carbons. We just learned our first reaction where we could remove carbons with ozonolysis. This actually gives us a way to add carbons. Because if we can make this and then put it with something that has a good leaving group, we wind up adding carbons to our system. So the way that gets shown is in reactions like this. Here's our strong base that's going to deprotonate our alkynide or our alkyne to make the alkynide. So we're going to leave this as our intermediate after step 1. Which then if we expose it to something with a good leaving group. That's yeah. So it's a halogen, so it's a good leaving group, right? I'm just going to write it out so we can see it a little bit better. SN2 never goes away. We have a strong nucleophile and a good leaving group. So we can do an SN2 reaction. It's just an SN2 reaction with a new type of nucleophile that we haven't seen before. That now adds a carbon on. So this is one of the other reasons why acetylene is such an important molecule, is because it's 2 carbons, but basically because it just looks like this, we can pull that hydrogen off, and this allows us to then stick it to something else. And then we can pull that hydrogen off and stick it to something else. So basically, it's a really convenient building block for linking things together and building more carbons up in a shape that's helpful for whatever reason.
So is this what we were doing there, or were you just drawing?
This is what we're going to do now.
Then up.
Yes.
So that's after. So what's the next?
So then what's the final step?
So is the.
This part stays the same. Right?
Right.
And then we added actual nucleophile to add here. So we added 2 more carbons. Basically, acetylene is one of the most important molecules in modern polymer production and chemical engineering, because it's a good way to start building these larger molecules up. And it turns out that's probably going to be one of the primary reasons that it's really hard to get off of fossil fuels. It turns out it's not actually driving cars. That's the biggest push to keep fossil fuels around, is because everybody's used to driving gasoline cars. But the process of petroleum refining also makes a lot of precursor molecules like this that then get turned into plastics that get turned in. This is one of the reasons why you hear people talk about that, or at least go to plastics that we can source from biological sources instead of petroleum sources. But we don't have anything at this point that's as good as the petroleum sources at making a lot of these things. And we use plastics in everything from silicon production to for making microchips needs plastic. It needs a lot of these precursor molecules to make a lot of the pieces in there. So it's not just like the obvious, like plastic cups and straws and things like that. It's also a lot of the infrastructure that builds a lot of the stuff that society is based on, also uses fossil fuels to make all those. And so we're looking for, there's a whole branch of chemistry called green chemistry that's dedicated to how do we replace these non-sustainable sources with something that's close to as good. And so slowly, chemists are aware of the problem of using petroleum. We also are just really used to, like, it's really nice to be able to use a nice pure acetylene as our building block.
Yeah.
So there's movement that direction as we find good alternatives. We're just not there yet. So that's one more reason why we still have petroleum being used. Even if everybody switched to electric cars tomorrow, we would still have a need for petroleum for stuff like this for now. So what if we do this twice in a row? If we started from acetylene, ethine, this one, exposing it to excess sodium amide, or just amide in general, it's going to do that.
Where the arrows?
Yeah. So we have NH2 with a negative charge. It's really strongly basic. So it grabs that hydrogen, and the carbon holds on to the electrons. So it's just a proton transfer step. Which then leads to this. And then the second step is, what am I going to add to it that has a good leaving group? So we're using the same molecule we did above, so it's going to kick the iodine off. So then we're going to make an intermediate here or we're going to make a molecule which we're writing it out, skeletal structure would look like that. So this last arrow is basically, okay, now let's take this and we're going to deprotonate the other side of the alkyne. We're going to say something else there. So our deprotonated form would look like that, and then we're exposing to just called methyl iodide or iodomethane. And do it again.
How did we become? Okay.
So we deprotonated it just like we did the first time. Instead of the other side. Because that's the side that still have hydrogen.
And maybe
So the NaNH2, that's just what deprotonates it. Exactly. You can see how that is pretty helpful.
Yeah.
This benzene, acetylene, and cyclohexane. Really, benzene and acetylene are the two most critical pieces for what they call total synthesis, which is where you're starting from scratch, which generally means you start from acetylene and benzene to build whatever you need. It's a lot trickier in some respects than starting from like a natural product. You can start, you're trying to make a molecule that looks kind of like vanillin. You start from vanillin and modify it. That's usually fewer steps, but you have to have a good source and a way to reliably get the vanilla and then extract the compound that you care about and purify it, which sometimes is actually more expensive than just starting from scratch and building.
Right.
So there are sourcing our stuff from natural products, as we saw in lab last quarter, has its own headaches when it comes to then taking it, purifying it, getting it ready to turn into something we can do some more reactions. But that's probably going to be what we see the most in the future. And if I'm speculating, probably where most synthesis is going to go is it's going to be all GMO yeast. Because it turns out yeast is really easy to grow in vats in reactors. And it's also relatively easy to add genes to. So if you can add genes to yeast to cause it to produce something yeast would normally have no reason to need, like that's actually where most insulin comes from. Yeast itself has no need for insulin because insulin is a chemical messenger in multicellular organisms, specifically mammals. Yeast is a single-celled organism. Why would it need insulin? But we take that gene and we insert it with some promoter regions inside the yeast, and the yeast makes insulin, and then it's pretty easy to remove. My guess is that a lot of important biological or important synthetic molecules for the synthesis pathways, we're going to start making them in yeast because that's a lot more sustainable and a lot easier to keep it going indefinitely.
Give it something and it runs.
Basically, we are pretty good at this point at being able to, especially if it's another natural product. Because if it's something that already is sequenced in a gene somewhere else, something else living, we can take that, add some promoter regions and add it. If it's something that doesn't occur naturally, that's a lot trickier to get it yeast to make a molecule that doesn't occur naturally in some other organism. Yeast is really good at accepting plasmids from other places, but Our knowledge of genetic modification is still probably not to a place where we could design a gene from scratch to make some molecule that's never shown up in nature before. I think that's kind of where it's heading, though, or at least getting it close to something that then we could take and finish it up chemically. Which is why bioengineering is such a big field right now. I thought bioengineering, I took some classes on bioengineering, and bioengineering is a big chunk of it right now is either tissue, how do I grow tissue from stem cells?
Right.
Or how do I insert a gene from one place to another for some desired output? Really interesting stuff. It does raise some ethical questions, especially once you start getting larger than single-celled organisms. That's another good reason to use yeast. Nobody's out there with picketing for yeast cells. But when you start getting into some of the more complicated molecules, you need multicellular organisms to make them. All right. You know what? Let's end 5 minutes early today. We've added enough. We've added enough stuff this week. Yeah. When we come back, we're just going to say, okay, alkynes and these have some similarities, but I'm not going to go through all of these mechanisms today. So that would make us a nice, clean place to start next week. Cool. Okay. So we will have a quiz this weekend. Cool. As usual. Watch for that later this afternoon or tomorrow, depending on when I have time for it.
And one file.
It's really not a big deal, but you can so totally do the whole thing, take a picture of it once. And if it gives you notifications, you can just upload the same file 5 times.
I think it's because you're worried, like, hey, you're missing a question. Do you want to submit it anyways? So you can be like, yes.
Perfect. Then that'll work.
So then I asked them, but they were very.
It's like those notifications when you send an email with the word attach, and then it says, it looks like you forgot to attach something.
Right.
Like, thanks for checking, but no.
Or like I'll use them with like attach or link like simultaneously. It's like, looks like it's link anything, but I attached to attachment and I'm like,
it's close. Have a good weekend.
And a piece for
Thanks, Amy. For you. Doing all right. I was just gonna take Laura up the workspace. Sounds good. Perfect. Thanks. Oh, thank you. You as well. Meet it. I'm waiting for Laura. Yeah, students first. She'll be here soon, I'm sure. Yeah. How's your term going? Yeah. Digging linear. Yeah. How's that going?
Busy,
Yeah.
but, I'm liking the chemical, balances.
I mean, it's overkill in most cases, but there are some weird situations where it's like a 17 to 29
Yeah,
cases, but chemists wouldn't necessarily go that route. But I can see why mathematicians be like, well, just do this, it's easy.
it can all be remembered.
Right. And the chemists are like, but that reaction is really 7 reactions in sequence. And if you just balance those, it all adds up.
Right. All right, I'll put this.
Hey, have a good one. Hey, Mike, how are you? Hey, how's it going?
I'm just hanging out.
Waiting for Laura. I'll say go to lunch, but hey, students first. Lots of stuff in the lunch, so
Hey.
it's actually just practical. Oh, we go. Yeah. Right. Yeah. Go take your time on that. But did she? Yeah. Awesome. Thank you. I just went up there. They said that she left, so she must be walking. Yeah. All right. No worries. I'll be there. Yeah. No, it happens. You you got hurt, right? Are you feeling better? Oh, it's been so icy. Oh yeah. Ouch. I'm glad to see you up and around. Yeah. The yeah. Yeah, yeah. Okay. That's I would prefer that. That's actually ideal. Because then you get to keep that and then I can't lose it. Saves my back. Yeah. Submit it as and some phones will let you save it as a PDF to do it all as one file. But if you just like the simplest way is just take a bunch of pictures, upload them as JPEGs, and you can probably do it right from your phone.
Okay.
If you have the Canvas app.
Okay. Yep,
So,
I do.
perfect.
Thank you.
Yeah, no problem. Let me know if you have any trouble with that, and we'll get it sorted. So you get the technology set up the way that works for you. Okay. It's already happening, so.
Okay, so